Hi, I'm Mr. Baker, and today we're going to be looking at force and acceleration. We're going to be looking at the Newton's second law required practical. Okay, so this is a simulation on the Focus e-learning website, which hopefully you'll be able to have access to and have a go at it. Now there's two parts to this required practical. We know that Newton's second law says that force is directly proportional to acceleration when we've got a constant mass. We also know that when force is constant, if you increase mass, then the acceleration is inversely proportional to that. And we did that last lesson, so if you're not sure about that, then go back to that. This is really just going through the required practical and what you've got to be able to do for that. We're going to go through one part of it, just looking at the first part. It's a very similar experiment for the other one. But remember, for the required practical, what you've got to be able to do is to describe the equipment that you've got to be able to use, and then look at how you might analyse those results. So let's go through the equipment that you'd have to have. So you'd have to have a ramp, so this thing here, and that ramp you'd want to make frictionless. So you could use an air track, and you could have a glider that goes across that, and you could set this up with that. Or if you've got a trolley and a ramp like this, then you would try and just raise the end of this very slightly, so that if you were to tap the trolley, it would just go down the trolley at a constant speed. Then with the trolley, you would hang that over the end of a pulley, which you'd put on the end of the ramp, and that would go down to a weight here. So this is going to be the weight that we're going to apply to the trolley. And every time you apply a weight to a trolley, so we're going to have a resultant force, which is going to be this weight. When you've got a resultant force, remembering back to Newton's first law, then you're going to make this accelerate. Newton's second law says that depending on the amount of resultant force, depending on the amount of weight that we're going to put on to that, then that's going to change the acceleration as well. So you're going to have a mask here, and you can see it's got two parts to this mask, because when this mask goes through the light gate, it's going to go through once, and then the second part's going to go through, and there's going to be a small time gap. So it's going to measure the time for this little distance to go through and work out the speed that it was going through here. Then it's going to measure the time that this little distance goes through, and then that's going to work out the speed that that goes through. So this is going to go through at one speed, and if it's accelerating, this will go through at a slightly faster speed, and so then it's going to be able to work out the difference between those speeds and the time gap between, and that will be able to work out the acceleration. So then this light gate will go to a data logger, and it will calculate the acceleration for you, and it will show you the acceleration. So what you're going to do as well, because we're going to be looking at the first part of this experiment where mass is constant, we've got to make this whole system that we're accelerating, we need to make sure that the mass is constant for that. So what we're going to do is we're going to put all our masses onto the trolley, and these masses are going to be hung on this stack here, and they're going to be the applied weight, the applied force. So this is going to be the force that we're going to be applying, but the mass is going to be constant. So I'm going to apply force, and then we're going to see it accelerate through, and then you would carry on doing this experiment. So let's do the first one. Okay, so you can see it's accelerating through for that applied force. So if you want to write down these results, you could do, or you could have a go at this in a minute. But the applied force there was 0.5 newtons, and the acceleration was 0.367 meters per second squared. And so you'd plot that point on your graph. Then we'd increase the force that we are pulling with. So now it's 1 newton, and it would be 0.689 meters per second squared. We'd plot that point on the graph, and we would carry on doing this with different weights, so different forces that we're accelerating it with. In this case, 0.966 now for 1.5, and we keep plotting those points on our graph. Now, obviously, if this was your required practical, have I just done the same one again? Haven't I? If this was your required practical, then what you would do is you would be filling in a table of results each time you did this. So for 2 newtons, it was 1.309 meters per second squared. And then you would plot the graph after. So 2.5 now is 1.656. 3 newtons, 1.942, and we would keep doing this. 3.5 newtons, 2.276, and you can see that this is kind of the trend that we would expect. 4 newtons is 2.669, because we know that as the force increases for a constant mass, the acceleration increases, and you can see it accelerating faster every time we add that on. So for 4.5 newtons it was 3.060 meters per second squared. Let's do the last one. Boom. 5 newtons is 3.305 meters per second squared. Okay, so if this was your required practical, you would repeat those results, and then you would try and make that a bit more accurate. So you could see maybe for this one, let's go, what, 4.5, it looks a bit different. Let's see if I did that one again. Will that plot a different point? No, I don't know. But you would do that again for different forces, repeat those forces over again, and then you would be able to average your results in your table and then draw the graph from the averages. Now your force goes on the x-axis, your acceleration goes on the y-axis, and then you would be able to draw a straight line of best fit through those, and then we'd be able to conclude that as the force increases, the acceleration increases. The line would go through 0, so we could then conclude that the acceleration is directly proportional to the force when the mass is constant, which is exactly what Newton's second law says. Okay, so talking about different things of this experiment, so the resolution here, like 3 decimal places, so it's quite a high resolution. To make it more accurate, so that's really talking about the precision. To make it more accurate, what we might do, like I said, is repeat the results there. The other thing we could do to increase the accuracy perhaps is to measure the mass here, instead of just taking for granted that each one of these masses is 50 grams, and then we'd be able to get a more accurate point there, so that we would know that exactly the force was on here that we're pulling it with, and that would make the point slightly more accurate there. And then your conclusion would be the same. You'd get the straight line best fit where the acceleration is directly proportional to the force. So hopefully you'll be able to have a go at that experiment, but for now that's the lesson done on the Newton's second law required practical, the forces and acceleration one. I've been Mr. Baker, and I will see you next time. Thank you.